Welcome back, everybody. Towards the end of the last lecture, we mentioned standardizing, but didn't explain what it is and why we use it. Before we understand this concept, we need to explain what a transformation is. So, a transformation is a way in which we can alter every element of a distribution to get a new distribution with similar characteristics. For normal distributions, we can use addition, subtraction, multiplication, and division without changing the type of the distribution. For instance, if we add a constant to every element of a normal distribution, the new distribution would still be normal. Let's discuss the 4 algebraic options and see how each one affects the graph. If we add a constant, like 3, to the entire distribution, then we simply need to move the graph 3 places to the right. Similarly, if we subtract a number from every element, we would simply move our current graph to the left to get the new one. If we multiply the function by a constant, it will shrink that many times. And if we divide every element by a number, the graph will expand. However, if we multiply or divide by a number between 0 and 1, the opposing effects will occur. For example, dividing by a half is the same as multiplying by 2, so the graph will shrink, even though we are dividing. All right, now that you know what a transformation is, we can explain standardizing. Standardizing is a special kind of transformation in which we make the expected value equal to 0 and the variance equal to 1. The distribution we get after standardizing any normal distribution is called a standard normal distribution. In addition to the 68, 95, 99.7 rule, a table exists which summarizes the most commonly used values for the CDF of a standard normal distribution. This table is known as the Standard Normal Distribution Table, or the Z-score table. Okay, so far we have learned what standardizing is and why it's convenient. What we haven't talked about is how to do it. First, we wish to move the graph either to the left or to the right until its mean equals 0. The way we would do that is by subtracting the mean, mu, from every element. After this, to make the standardization complete, we need to make sure the standard deviation is 1. To do so, we would have to divide every element of the newly obtained distribution by the value of the standard deviation, sigma. If we denote the standard normal distribution with z, then for any normally distributed variable y, z equals y minus mu over sigma. This equation expresses the transformation we use when standardizing. Amazing! Applying this single transformation for any normal distribution would result in a standard normal distribution, which is convenient. Essentially, every element of the non-standardized distribution is represented in the new distribution by the number of standard deviations it is away from the mean. For instance, if a value y is 2.3 standard deviations away from the mean, its equivalent value z would be equal to 2.3. Standardizing is incredibly useful when we have a normal distribution. However, we cannot always anticipate that the data is spread out that way. A crucial fact to remember about the normal distribution is that it requires a lot of data. If our sample is limited, we run the risk of outliers drastically affecting our analysis. In cases where we have less than 30 entries, we usually avoid assuming a normal distribution. However, there is a small sample size approximation of a normal distribution called the student's t-distribution, and we're going to focus on that in our next lecture. Thanks for watching.